So from the previous one, Kate,
Yes.
what is an element?
Element is the small, it's like a grouping of.
Is like or is?
It is a grouping of atoms that are all, that all contain the same amount of protons. And so they have certain characteristics because of this amount of protons that they have. And it's just, all of them are atoms, but they're like grouped together.
Okay, how many elements we have in the periodic table, Horacio?
118.
Sure?
Or,
You remember that we talked about this?
okay. 115.
Okay. Harsh, how many groups are in the periodic table?
3
Which one?
metals, non-metals, and metalloids.
Okay, so there's a kind of a division that they use for the periodic table. Harsh, are you familiar with this division?
Yes.
So what you can tell me about the P block?
The P block has all of the metalloids in it, and it also has some regular metals, and it also has the gases.
Okay. Kate, what you can tell me about the P block, no, the S block?
The S block has one valence electron and the electron. Well, one valence electron.
Are you sure?
Well, except for helium. Helium has 2, but it's on the other side of the thing. It's just pause. The inner shell thing is 2. Let me think about this.
Yeah,
It's been a long day.
like, yeah.
I remember going
understand.
into this.
Check here in the bottom.
But they just have like, they're,
1s1, 2s, 1s.
they have 2 electrons. And they're atoms.
No. What happened with the, what is the name of this group? Horacio, the first one. What is the name of this group?
The S block.
No, only this group.
That's the alkaline ones.
So, how many electrons in the outer shell it has? And then the next one,
Alkaline electrons.
how many electrons in the outer shell?
Like, why are those 2 put together?
Sorry, because they're S. This is called S block because the electronic configuration finish in.
Well,
Okay,
I know
Horacio,
that.
what you can tell me about the D block?
That's the transition metals.
That's
And one they call this the D block.
Because their electrons are going to fall in the d orbit.
The outer shell.
Yeah, the valence electrons are going to fall in the d orbit.
Okay, perfect. Harsh, do you know these guys here?
Yes.
What you can tell me about these guys?
They are the F block, and they are the. I always try to avoid those because those are like this segregated out of the periodic table.
Why do you want to ignore them?
I
Don't you
don't
like?
know. We don't learn a lot about them
Why not?
because they're not that common in like things too much, in like experiments or like reactions.
Okay, kind of. You know the name of them? They have this part has one name and the second part has another
It's like
name.
a weird name. One of them starts with like a L, like a Lawrence or something, or does one of them
Kate, do you
start
want to
with
help him?
F?
You are right, it does start with an L, but it rhymes with, is it lanthanides? Is that what it is? Lanthanides.
Lanthanide.
On the second one there.
It starts with A.
Lanthanide.
So you can give a guidance because you see the first element is La and the first element of this group is AC. So this is the lantane, I think in English. And so this is the lanthanides and this is AC. So this is, what is the name? Okay, actinide?
Actinides.
Actinide. So then we talk a little bit about the periodic table trends. So in the periodic table, we have a perfect arrangement of things that are very well organized. And then we can talk about several characteristics that we are going to find because of this organization. So one of them is called the shielding. Horacio, what is the shielding
those are the like inner electrons. So those are gonna be like yeah.
Shielding
So,
is like an effect.
yeah. So like instead of when you have like the nuclear like effective nuclear charge, you're only talking about like the valence electrons. So all the electrons that are like in the inner shells. So like if you have trying to think of an example like sodium for example. So the first two electrons in like the first shell, those are going to be your shielding electrons because they block part of the nuclear charge from the valence.
Very good. So, Kate, could you tell me about the effective nuclear charge? How you can calculate this? Could you calculate this?
Yeah, you can, I think you do the total electrons minus the shielding ones.
Are you
and
sure?
see the
Okay. So, Harsh,
Yes.
you have here, this is like a model of an atom, right? So, in the center you have a nucleus,
Mm-hmm.
and this nucleus has 9 plus. What means that they have 9 plus?
Has 9 protons.
Yes. So, and then you see that they call this thing like helium-filled shell, and it has 2 electrons.
Yes.
How many electrons has helium?
2.
So then they talk about the neon shell. So how many electrons we have in the neon shell?
Neon's a noble gas, right?
Mhm.
So 8.
You have,
Oh, 7.
okay.
Is neon a noble gas or halogen?
Neon shell just refers to the fact that it's like part of the like after neon or
So,
like before neon.
This is related with this because yes, it's a noble gas, but it's related with this. Like this has 1, this has 2, this has 3, 4, 5, 6.
Okay.
So that's the reason because they call this the neon shell. And then in this case, Harsh, which electrons are going to experience more the effect of the nucleus? The electrons that are in the helium shell or the electrons that are in the neon shell?
The neon shell,
Why?
because they are the valence electrons, so they would experience more of the. Wait, what was the question again?
Kate, could you help Harsh?
What is the question? Sorry, I'm writing notes down.
Did you hear the question, Horacio?
Oh We're writing notes.
So, which electrons are going to feel more the effect of the nucleus? The
Oh.
helium
Oh.
or the
The helium
neon?
one.
Yeah, I didn't think
helium
about the
one.
question. Yeah, the helium ones, because they were closest to the nucleus.
Ah, okay. I was worried. Okay,
I zoned out.
We're writing notes.
okay.
Have a little notes.
So, and then you can make calculations about this. It's very easy actually. So, it's an addition.
Wait,
So,
if something has more, like it fills the 2 electron shell and the next electron shell, would for the effective nuclear charge, would you subtract all of the inner shells?
yeah, remember this. For example,
Mm-hmm.
let's talk about chlorine. So the chlorine has this configuration. So, and they talk about shielding electrons. So,
anything not in the valence shell?
yeah. So you see, they have in the first, how many electrons they have? 2. In the second, they have 8 in total, right? So these electrons are going to be the shielding electrons. The shielding electrons are going to be the one that cover the nucleus. And then the effective effect. So how many valence electrons has the chlorine?
7.
7. So these 7 electrons that are outside are going to be the electrons, let me show you here, that are very far away actually. So they're not going to feel the effect of the nucleus because all these electrons that are here in the shell, in the neon shell and in the helium shell are going to cover the effect. This answer your question?
Mm-hmm. Yes, sir.
Okay. Then we talk about periodic trends. Do you remember periodic trends, Harsh?
Yes.
What do you remember?
I remember that everything increases across a period except size, and everything increases down a group except size.
Okay, so,
Atomic radius.
what about the effective nuclear charge? How it is affected through the periodic table?
It increases as you go across a period or down a group.
Okay. Let's see, and what about the distance between the valence electrons and the nucleus? How this increase in the periodic table?
Well, across a period, they would the distance would decrease, and down a group it would also decrease.
Horacio, what is the biggest atom in the periodic table?
The biggest atom is francium.
Kate, what is the smallest one?
Hydrogen.
No,
In the periodic table?
it's not hydrogen.
Is it- Oh, it's helium. We went over this. I
Kate is
forgot.
tired.
I didn't
You
know.
see? What happened when the people don't sleep?
I do know.
Okay, so, as Hart was saying, the periodic effect increase like this, and then increase like this. Right? That's what you said?
The ZEP. Wait, what is the ZEP again?
That's effective nuclear charge.
Yeah.
Okay, this confirms or not? So then we have different properties. So, Horacio, what is attraction?
It's basically like the effective nuclear charge source. So it's like what is like the like attractive force in between the nucleus and all the and the valence electrons, like charge wise.
Okay, and how this change in the periodic table?
Hold on. It like goes as you go like down a group, it's gonna be less because you have greater distance, and then if you go across a period, it's gonna increase just because there's more electrons.
Okay. Kate, what you can tell me about the atomic radius? What is the atomic radius?
It's the radius of the atom.
Could you be more specific? How you can measure this?
Well, the distance from the nucleus to the valence from the nucleus to the valence electrons.
Which units are this?
AMU, isn't it?
What?
Isn't it AMU? Is that
AMU?
That's mass.
that's
AMU is
that's
mass.
something. Oh, I know it's not inches, so
I mean, it'll be inches, but you have a lot of zeros.
yeah.
That's,
Um,
so which unit we use to measure the atomic radius?
Is it nanometers?
aren't those
Is
two
it
ways?
It
micro?
could be, but it's
Are
not
those too
very
big?
frequent. Because nano is minus 10 to the minus 9.
What is
and this
micro?
is really small.
Is micrometers bigger than nanometers?
Yeah.
Okay.
Nanometers is 9, micrometers is like
What is smaller than nano?
No.
deca.
That is
Deca.
Nope, that's
Deca?
10. Well, nano is
We're going to do a GoFund for Kate to drink and coffee today.
thank you. You know what? I'll take it.
They
Not
have
a kilogram.
picometers, femtometers, atometers,
Excellent.
septometers.
Picometers or Armstrongs?
Okay.
Armstrong?
Armstrongs is a unit that is 10 to the minus 12.
See, that's what I was thinking, but I was just wrong. Picometers? Oh, that is so cute.
Okay, now harsh.
Yes.
What is electronegativity?
Electronegativity is the ability of an atom to attract an electron in a covalent bond.
Okay, I have a question for all of you. What are the units of electronegativity?
Attraction.
Charge coulombs.
No.
Could be like a unit of force.
Electronegativity, ability of something to attract. Charge.
It's force. It's not going to be newtons.
I don't know. I did not take physics. They was in 10th grade.
I took physics in 10th too. I don't know.
Most of the time I had in the bucket.
Any idea, Harsh?
No.
Horacio, any idea?
I have
Not a clue.
know.
Kate,
What?
any idea?
No, ma'am.
No. Okay, so the electronegativity don't have any units because it's a relationship.
That is a trick question. Well, it says the Pauling scale.
Yeah, there's
But that's
several
like
scales
the
actually.
same.
It's not only
Yeah.
there is the Pauling scale, then the Fermi scale, then there's whatever person that wants to be fancy create an electronegativity scale, because you can find actually many periodic tables that have different values of electronegativity, and then you get
UN
crazy
scale.
with this. So usually, I'm actually didn't check yet in your IB program which electronegativity they use, but usually in the normal chemistry books they use the Pauli electronegativity. That actually is a relationship. So
Yeah.
Harsh,
So Google.
which is the most electronegative atom in the periodic table?
Fluorine?
Kate, what is the less electronegative atom in the periodic table?
Maybe lithium? Why do I get all the bad questions?
Horacio?
Hold on, I'm trying to think. If it's fluorine on that end, would it be cesium?
Yeah, exactly. Or francium?
Yeah, or francium.
Yes, Kate.
Wait. No, wouldn't.
Because everything decreases down a group.
Yeah, but.
So
You look
check
at
this.
straight, like you look at the
The
corners.
most
Look at the
electronegative is
corners.
this one, so the less electronegative is this one. It goes here.
But I
and
would
here.
have thought electronegativity is the ability to attract an electron to form a covalent bond. Lithium
Yeah.
does not want to do that
But it's not
Yeah,
only
but
covalent bond,
cesium
it's to
would
form a
not want to do
bond.
that
Whatever
more.
bond.
because it's farther. Okay.
Yeah.
All right.
Okay.
Crappiest questions.
So the ionic radius. So Harsh, what is the difference between atomic radius and ionic radius?
Well, atomic radius.
It's definitely not
Oh,
cesium.
wait,
Not you. No. Cesium.
I would feel like ionic radius would deal with ions, like when an electron is removed, and an atomic radius is just a regular atom.
Exactly. So let's give another opportunity to Kate. Kate, let's say that we have. Oh, I don't have.
Give bad question.
We have a cation that is formed from potassium, the favorite element of ours.
Oh yes. You know my name can almost be spelled except there's not an E.
Yeah, I know.
I can spell my name.
So now my question is, if I compare the radius of the sodium atom with the radius of the sodium ion, which is bigger, the ion or the atom
Sodium?
for
Hmm.
sodium? No, for potassium. Sorry.
Either
That's it?
one.
Yeah.
They form the same type of ion. The ion would be smaller.
Yes.
So the atom would be
This is
bigger.
my question.
Oh, I'm sorry. I didn't hear you.
Yes, the ion would be smaller.
Why?
Because as it loses an electron, it loses that outer shell. So it's like
Okay, only for Kate.
Big time.
We are going to do now ion with bromine. Is bigger the bromine ion, or the bromine atom?
just the atom would be bigger.
Why?
Because if you add that extra, or when you have that extra electron, the charger, the effective nuclear charge goes to, I think, it would go to 8 or 0, I don't know, but it would squeeze it tighter because there's more of them.
Wait, what ion is it talking about? Remove it?
Bromine.
Electron or atom?
You're adding an electron.
Oh,
to it.
okay.
So because there's more, it's going to squeeze tighter together.
Wait, everything
Okay.
increases across except size.
For atomic radius, but we didn't learn ionic radius.
Okay.
Or at least we didn't learn it in the context of the up and down arrows.
Okay. So there's another trend, periodic trend that is called the
Oh,
first
right.
ionization energy and the first electron affinity. So, Harsh,
Yes.
what is this first ionization energy?
First ionization energy is the energy change when 1 mole of electrons is removed from 1 mole of the gaseous atoms.
How do you know these things?
It's on the.
In your brain.
It's in my brain and in my heart.
In your heart, especially. Very
Yes.
good. And how this change in the periodic table?
This is like the same. It increases across a period and decreases down a group.
Okay. Horacio, what is the first electron affinity?
It's the energy change when 1 mole of gaseous atoms requires 1 mole of electrons to form 1 mole of gases 1 minus ion.
Okay, very good. How would they change in the periodic table? It changed in the periodic table.
Electron affinity. It so as the attraction goes up, it's gonna have like the same trend as the attraction basically. So as the attraction goes up, the electron affinity is also gonna go up.
Okay. So I have a question for Kate again. Another opportunity, Kate. What is the definition for second ionization energy?
The energy change when an additional mole of gaseous atoms acquired.
How many moles of electrons?
Additional, huh?
How many moles of electrons we remove?
Two.
Okay, very good.
Yes.
Fantastic.
Thank you.
We made this example. I don't know if you remember in this point of their life, what is the answer of this? Oh, you want to try?
I remember arguing over this. It's in my
In
notebook.
decreasing size.
Oh, wait, we have it here. Yeah, it's in purple. That's because I colored.
You want to try, Harsh?
I would need a periodic table for that. It'll be really handy.
Do you have a periodic table? How do
You
you
don't
come
have
to
it
chemistry
memorized?
class without periodic
Yeah,
table?
man, come on.
What?
Have it memorized.
I don't have it memorized.
No, but don't worry. On Monday you already have to memorize. Do you know what Harsh has to do for the next week?
Yes.
What is it?
Do you want me to
I
say
have
to
to
them?
recite a periodic table song because I got it messed up the elements.
Do you know the periodic table song?
Is that what you guys did in 6th grade?
No,
There
what
was
we
a
did in
teacher
6th grade was
Who made them do the? I swear
Only for Harsh.
to God.
Kate's gonna sing for us
Heck
actually
no.
in class.
No.
She
I
said
refuse.
that she is willing to sing for
I
us
think
tomorrow.
Horatio, Tristan Paint, and Brian Park can all do a 3-part harmony for this song.
We really can't.
They would, and I
We
don't.
can only do it if it's a 4-part with Sebastian.
So, but yeah, Sebastian too, and Diego can be the soprano. No, he can bass. I don't know.
Diego would, no, we need Jody as bass.
Jody is bass.
Okay, are you ready? Harsh.
So
I
ready.
Yeah.
am.
This is especially for you.
Oh goodness, do you have to sing this in front of the whole class?
You
You
gonna
should
memorize?
dress
Are
up.
you gonna memorize lyrics?
Are you getting extra credit or anything, or are you just doing this?
Am I getting extra credit?
Good question, Charge.
I say.
I say yes.
Hey,
Hey,
ready for that 9:30 meeting?
almost. Wake up to your Wawa favorites.
Wawa
But he just ditched her.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, oxygen so you can breathe it, fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable, halogens and alkali react aggressively. Each period will see new outer shuffle, the electrons are added, moving to the right. Iron is the 26th, and cobalt, nickel, points again, copper, zinc, gallium, germanium, and arsenic, selenium, and rhodium, krypton, calcite, rubidium, and strontium, and yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits. Well, lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62 samarium, europium, gadolinium, and terbium, dysprosium, chromium, erbium, thulium, terbium, lutetium. stone, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead the biscuit for your tummy, polonium, oxygen would not be yummy, radar, and cesium will last a little time, radium, then actinize at 89. This is the periodic table, noble gas is stable, halogens and alkali reactor recipe. Each period will see new outer shell electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, titanium, chromium, aluminum, nobelium, lawrencium, rutherfordium, wdium, scorpium, borium, hesium, meitnerium, neptunium, mercurium, carbonicium, nihonium, flerovium, moscovium, livermorium, tennessine, and organesson, and then we're done. Thank you guys so much for watching. If you like the song, make sure you check it
I
out.
don't think the whole thing.
That was so good.
Isn't it just the first minute 30?
Yeah, you need to learn only the first minute, 1 minute 20 or 30 seconds, I told you.
Okay.
That
Or
is
if you
so
sing it like at 3 times speed,
good.
you can do the entire song, man.
Oh my goodness.
Honestly, if I just keep playing that over and over, I could probably memorize that.
I'm like yelling at my.
Okay,
This is so good.
you see? And almost all my pre-IB kids learned this song. So, now, but do you think we can do that?
Oh.
You got this, bro. Yes.
So-
Would you like it in song form?
No, thank you. It's fine, I can just. Okay, so Ne is there, F minus.
What is NE?
Neon,
Ah, okay.
and fluorine is. Okay, and then Na. Okay, they all have like, they're all stable. So Na loses an electron, so it'll be very. Actually, yeah, it'll be smaller, I guess. Na would be very small because it'll lose an electron. F minus would be, okay, F minus Ne. Well, as you go across, it decreases. So I think it would be Na, F, and then Ne. Well, Na plus F minus and Ne.
Write down the electronic configuration of each atom. Because I think it's going to be useful for this. Do you have the answer?
Wait, how do you want me to write down the electron configuration?
As
Like,
the way that you want. You can write down, for example, a Bohr diagram.
Bohr diagram. for that.
I think the best way to see the change in the size is with a Bohr diagram.
I just got mine renewed. Oh shoot, I have to use those for my thing though. History item. That's so weird. I would be able to. I might just make an account.
I'm not paying for it.
It costs money.
Yeah, I think so.
Yeah, Britannica costs money, and it's really.
And so, let's have a look at it. Wouldn't that be so fun? Public lifeguard?
I was gonna do it, but I keep
said what does it mean, not how do you say it.
Berry.
Pardon?
Berry.
Let me know when you're done.
That's Purdue.
Purdue is the same as berry in Spanish.
Oh. Well, I didn't realize you were translating
That's like
Spanish.
the berry thing.
I lost my ability to fight
No.
in English. Parlay. Parlay.
And it would be the smallest.
That's
one.
Ablar. Or Desir.
In Portuguese, it's falar.
I know.
It's similar.
What about that one?
Yo no sé.
Yeah, would it be,
You don't even know.
Okay.
Okay. Okay,
So
but
what
like,
is the order?
I
What
think
is
it's
this
just
one?
the NA plus F minus NE. That's what I think it would be.
Okay, what do you think? Agree?
what were you say, sorry?
Oh wait, decreasing size?
Mhm.
No wait, NA plus NE F minus, I think.
Horacio, what do you say?
No, I like that.
Okay, what about the second part of the question?
Explain what these are. Isoelectric, electronic. What does that mean? Isoelectronic.
What means the, Kate, what is isoelectronic?
Hmm?
What is isoelectronic? What
Oh,
it
they all
means?
have the same electrons.
Mm.
Or the same amount of electrons. And they're
Same amount of
balanced.
valence electron.
Yeah.
Essentially, they're all gonna have the same effective nuclear charge.
Excellent.
That's not what the definition says.
Very good.
Two electrons.
Very good. Okay, so.
You have one, you have to have the other.
Then we can talk about a little bit about the melting and the boiling points of the elements. So, the melting point of an element is going to change according with the number of electrons that we have available. But we are going to talk specifically of the alkali metals. So, do you remember the definition of metallic bond?
Isn't it like, wasn't it,
Positive. It's positive metal ions.
I remember like
And then
C of
a
electra
sea
and
of
C of
electrons.
delocalized electrons,
Uh-huh.
that's what I remember.
So, how we are going to increase the strength of a metallic bond?
You add
Increasing
more
the charge density.
So what it means in the sea of electrons, that we are going to increase what?
Like the density, so like,
So what is density?
it's
Charge
like
density.
charge density is like how much of a charge you have in like a specific space, kind of,
Yeah. So how you can increase the charge density?
by adding smaller atoms that have more valence electrons.
So, and then with this, how, which atom in the alkali metals has the highest melting point?
The highest melting point, it would be the first one, so sodium.
Sodium. So they said at the end here, less predicted to have the highest melting point and the boiling point. So, yeah. So in the case of the halogens, they form apolar molecules. It's mine. Sorry. So then the only molecules that are, or the only forces that are going to be available are the London dispersion forces. So I have a question that was actually asked to my to the juniors, because we are looking for solubility and things like this. Do you know what kind of compounds are soluble in water?
Polar.
Polar ones, yeah.
Okay. So how a fish survives in the water? How it can breathe?
With gills.
With what?
Gills.
But how is present in the water?
Oxygen
Dissolved
is
oxygen.
dissolved in the water.
But is oxygen a polar molecule?
No,
No.
It can be, I guess.
no, it's not. Oxygen on its own is not a polar molecule. It's gonna be like,
Well, it's in there as O3 or O2.
O3, that's
O2.
ozone.
it's gonna be
Sorry.
an
You're going to kill the poor fish.
It's
So
in there
how
as
is this
O2.
is possible? Because the oxygen is soluble in water.
It can be polar in certain situations. Like it's not constantly like
What is the name of this?
You know what I'm talking about. I just can't think of the name of it. It's
Yeah.
You have London dispersion,
no, it's
random assortment of electrons.
No, it's only when it's polar for like a certain, certain.
That's why like some
Orientation.
polar instantaneity or what? That's not the right word at all. But it's that idea. Like it at a certain point in time, it can be polar, which allows it to be dissolved, like an unequal sharing of the electrons. But I don't remember the word for it.
Dipole,
I didn't think that was right.
induce, or instant dipole.
That's what it is. Dipole. But I thought it was dipole interactions, which does make.
No, this is the name of the force.
Yeah.
Actually, it's dipole in instant dipole. Because as you mentioned, yes, the oxygen is not completely like the behavior of the electrons in a molecule, in a dipolar molecule, is not like always is going to be the same. Sometimes it's going to move, sometimes it's going to move to the, for example, for the left oxygen and the other time in the right oxygen. But in average, it's going to be polar. But because of these temporary or instant effects, these allow the molecule to be soluble in water. Interesting, no? So, what about the chemical reactivity? Horacio, what are the more reactive metals in the periodic table?
metals, the alkali.
Why?
Since they have one electron in their valence shell, it's like very easy for them to just get rid of it. So they have a tendency just to like become that the ion, and it's easier for them since they only have to get rid of one. It takes less energy than the other thing.
Harsh.
Yeah.
What are the most reactive non-metals in the periodic table?
It would be the halogens,
Why?
because they're also one electron away from being stable, from having a full valence shell. So since there are one electron away, that doesn't require a lot of like energy to put that electron in there. So they're kind of like the same as the alkali, except like reverse. They need extra electron, except to get rid of one.
So, in this order of ideas, what is the most unstable element of the periodic table?
The noble gases.
Really? Unstable?
Stable,
Unstable.
unstable,
Mhm.
unstable gases.
No, element.
Oh,
Kate,
Fluorine
fluorine, are you sure?
or cesium. Well, that's reactive. So unstable would be fluorine. Yeah.
What do you say? Well, your vote goes with which element, Horacio?
What?
Most
Which is the
unstable.
most unstable element?
Unstable element?
yeah, it would be.
So the situation here is what brings stability to an element.
Full
Or
electron.
full
Wouldn't hydrogen?
Do you remember that we talked about the island of stability?
No.
No, you don't, because you weren't.
You weren't
You
there. You're not
you
supposed to
you,
remember.
you forget us.
You did.
I know I had
I mean,
stuff to
like,
do. I had like golf and
Stability and
other
reactivity,
meetings to
would
do.
those like be different? Cause like you could say like the least stable would be like a radioactive element just cause it breaks down.
Oh,
So something like uranium or something. Or
Francine.
plutonium.
So remember that the reactivity is not related with the stability.
Yeah.
Mm-hmm.
Just
Stability, what is it? So the thing is, what is stability?
It's the
It
ability
It
of
deals
an
with the
atom to
valence
stay together.
electron.
stay as it is.
And what is reactivity?
The ability of an atom to react.
With another one, or multiple other ones. Is it that Francine one?
Francium.
Sorry, it is Francine. We wrote Francine here, which
I think maybe it could be in between francium and another uranium or something like this, because
Cesium.
there's some atoms that has
Yeah, that
so
was weird.
many. Actually, the stability is of the atoms is to the balance that you have in between protons and neutrons.
couldn't you say the most unstable ones are the ones that like haven't been like found or formed yet? Because like they're not even stable enough to be put on the periodic table,
Yeah,
right?
like element 1-1.
Even though you know
Yeah,
they're there.
it's could be, it's fair this, because actually the new elements that they are discovering now, they have lifetimes that are extremely short. Actually, we are talking about picoseconds, nanoseconds. So
It's like shorter than francium.
yeah, so francium you can have like francium,
Francium doesn't decompose.
Yes, it does.
but you cannot buy,
Yeah,
for
it does.
example,
You can't have a
Yeah,
francium.
something.
Yeah.
one of these, the element number 110, you cannot buy in a store.
Yeah.
So this is a valid point, Kate. Now, all
Yeah,
your
is those-
sins are forgiven now.
Thank you. Look at that.
You could rephrase the question, what's the most like stable natural element? Because the ones we made
Yeah,
are not natural.
Yeah,
Like, they
because
don't
the others are
exist
synthetic.
anywhere except
uh-huh,
Earth.
yeah, that's great. Good, Harsh, good.
Oh, look at that. We're brilliant.
So, and then we have all these reactions that hopefully Harsh is going to learn.
Yeah, Harsh.
Mm-hmm.
Because I saw many strange reactions today. Many.
Mm.
So we have, when we mix an alkali metal with water, what is going to form? What is the name of this compound? In general.
Base.
Sorry?
Yeah.
Oxide.
Lithium
Metal
oxide.
oxide. Metal oxide.
What is this?
Oh, that's lithium oxide.
Lithium what?
Oxide?
What is this?
Not oxide.
Horacio, what is
Oxide.
this? What is the name of this compound?
Lithium hydroxide.
Yeah.
Thank you so much.
Hydroxide. I forgot the H. God, be nice.
I forgot it too.
Thank you. I'm trying my best here.
Harsh, which element is this?
Sodium.
I'm not going to mention any. And then we can have, for example, so they have different types of reactions. So we have the alkali metals with water are going to form hydroxides, always, or bases. When you mix an alkali metal with halogen, it's going to form what? What is this in general? What type of compound is this? Hard.
Maybe halo.
Hmm?
What was
Okay.
What are
it?
you looking at? Sir?
Halogens plus.
What?
Salt.
Oh.
Yeah, salt. And then we have this kind of displacement reaction. So we have a salt, and then we have halogen, for example, and then the bromine that was here is displaced for the chlorine. Easy. And I think we already saw this video. So now we're going to see the transition metals.
Ooh.
That are the favorite of, I think, Horacio, you like the transition metal, right?
Not really.
But,
They're confusing.
okay. So, the transition metals are atoms that have an incomplete D subshell. So, and thanks to this, they're going to have many characteristics that are very interesting in terms of chemistry. And actually, there's a branch of chemistry that is called coordination chemistry that study very, very deep all the chemistry that involve the transition metals. So, and this is more interesting. So, we have, for example, in terms of zinc. Zinc, the electronic configuration of zinc is this one. But when we have the anion, if you notice, we didn't change the number of electrons in the D shell. It's the same, D10, D10. Because actually, when we form the iron, we're changing the valence electrons, and the valence electrons are in the outer shell. Interesting. So, and the situation here is that because of this effect, and especially because of this incomplete D subshell, we are going to have many different oxidation states. We can have, for example, in the case of iron, we can have +2+, 3+. In the case of copper, we have +1, 2+. So we cannot establish like a regularity that as we had before with the alkali metals. We already know that all the alkali metals are going to be +1 or 1+. And the alkali earth, how do you call this? Alkali earth?
Alkaline earth metals, yeah.
In Spanish it's so different. Alkalinoterres.
That's cool though.
The alkali earth are going to be all plus 2. But here you have a variety that nothing to do. So, and because of this ability that they have, this possibility that has like an open position in the D shell, they can form something that we call complex ions. So the complex ions are molecules that has a central atom, and then we are going to have molecules that are called ligands. Ligands or ligands?
I don't
I
remember.
don't know.
Ligand,
We have.
I thought these were water.
Don't worry, I have this one.
ligaments.
Oh my goodness. No.
Ligands. What?
In Spanish.
Ligandos. Yeah. Somewhere.
So the ligands are going to be molecules, and could be two type of molecules. Can be neutral molecules or could be anions that donate a non-bonding pair of electrons, and they're going to form something that is very special. They are going to form something that is called they have several names for this. This bond, if you notice, they have a special notation because it's not like a regular bond that is only a line. In this particular type of bonds, we are going to find an arrow that is going to show us who is the atom that is donated and who is accepted. So, for example, in this complex that we have with aluminum, the water, or more specific, actually, the oxygen is donated 2 electrons to the aluminum. So this is, in some books you can, they say that this is a particular case for the covalent bond in between these two elements. But the problem here is, in a normal covalent bond, you're going to share electrons. But in this case, actually, there's no sharing. Only the ligand is donating electrons. The aluminum is not doing anything. It's only accepting, okay? And then we can calculate something that we call the coordination number. So the coordination number is the number of ligands around the central ion. So what is going to be the coordination number for aluminum?
6.
Yeah, perfect. And what is going to be the charge of the complex?
3 plus.
Yeah, perfect. So, and the situation here is because the water molecule is neutral, it's not going to affect the charge. But if we have anions, they are going to affect the charge. So, and depends on the ligand that you have in the molecule, you can have actually something that is very interesting, and it's called the spectrochemical series. So, the ligand, according with the strength that they have, is going to give certain color to the complex. So, for example, I think it's better with a video because this is going to be like very not easy to understand. But let me explain the spectrochemical series. So, if you notice here, we organize from the iodine, from the, what is the name of this ion, Horacio?
What do you mean?
This, what is the name of this ion?
Via carbonitrate?
No, next, harsh. What is the name of this ion?
I don't know.
K.
Cyanide.
How do you know?
What?
I'm brilliant.
Oh yeah, she memorized all of those.
No, this was on the what's it called? The test, the quiz that we had, the very bad one with the structures. Because I went home and I looked it up. Well, it was HCN, and I went home and I looked it up and I was like, what is this? And then I just looked it up again because I was like, I just looked this up not too long ago.
Cyanide?
Very
Yeah.
good.
When you burn water bottles, this stuff comes off.
Actually, this is like the most popular version of this iron is in form of an acid. So this is called, what is the name of the acid? HCN.
I don't remember. I literally looked
It
this
was
up.
in the quiz.
I know, and I was so frustrated because I couldn't figure it out. HCN hydrogen cyanide. See?
So difficult, you see?
I got the hydrogen part, but it didn't.
So, and actually this compound is very popular because I don't remember now who was the person who was killed, but there's a compound that is called cyanure. It's the word in English, cyanure. And the cyanure is an extract for a plant. And there, let me see, how is it? The name in Spanish is cyanure. So, the cyanide actually is an extract of a plant, and the thing is, you can poison somebody and nobody can know how was dead this person. And it's very quick. Like you eat a little bit, I don't remember right now what is the LD of this, LD50, but it's only a little bit and then you immediately. And there's actually, as far as I remember, normally when a person pass away because of a chemical poison, they can track this in the blood. But the speed of disappearance of this compound is very quick. So the only way that you can track this is in the hair.
The hair?
Like, it would have to be the roots, right?
Yeah, because you know that when you pass away, everybody's going to pass away, so please don't be scared, but this is a sad reality, but it is.
I'm not dying.
So
You're not dying.
when you pass away, there's two things that continue growing.
Hair and nails.
Uh-huh. So in the hair is going to appear the cyanide.
So if you kill a bald person with cyanide, you'll never be caught. Is it
So-
the same for like other hair too, like facial hair, leg hair, like?
I'm sure that this hair, but I'm not sure about the other hairs. I think probably because I think it's the same effect. I have to ask to somebody. And the interesting thing is, you know, in which other place we can find this kind of compound? Do you like peach?
Peachy?
My mom
Peaches.
loves
Oh, does the
peaches.
seed peach have the cyanide?
Oh.
Yeah.
Cherry
Cherries
seeds.
have it.
Cherry seeds.
Wait, don't
I've heard that
It's
before.
not
apple
like,
seeds
it's not like
have
in
it?
the seed itself. It's like when it reacts in your stomach and metabolizes into it.
Don't apple seeds
So
have
when the
something
people
that's also
like
very
to,
bad?
Yeah.
love to eat these seeds and they keep the seed inside of the mouth several like hours and hours,
Mhm.
you know what can happen?
I thought you had to like break it because I think like this.
Yeah, I think it's
isn't it, like,
inside.
Yeah, but maybe you can do like when you have in your side of your mouth you can
Chew
buy
it.
this thing,
And like squeeze out the inside.
and then if you keep this thing 2 hours in your mouth,
I don't know who does that though. That's like weird.
so only to let you know. So let me show you the video.
I just get reminded of
Okay, cool.
cyanide and happiness whenever I think
So,
of it.
well, so this is like several ligands that we can have. So whatever of this ligand can be put in the same position as the water is. Interesting, no? And then actually we are going to have, like for example, if we can predict what is going to be the color. So if we have, for example, a compound that has water as a ligand, it's very probable that the color is going to be in this region,
And that's just what it looks like?
Blue?
the color.
Like the solution? Or?
Yeah, the compound solid is this color. So for example, this is going to be, it's very probable that it's going to be blue.
So is that where we get like hydrates and stuff like that, and we get like copper hydrates?
Exactly. For example, this is the typical laboratory that you did, I hope.
Which
Sulfate, what is the name of this? The dehydration of copper sulfate.
Oh, yeah.
Degradation of
Mhm.
cop-
You
yeah,
remember
I
that
think
you
it-
have the copper sulfate?
Copper sulfate
Didn't
with
Yeah,
it
because
blue.
literally it's
burned-
like
it
copper.
burned
You get like
green.
like you start out with like copper sulfate pentahydrate, and that's
And-
normally like a bluish green color. Then when you dehydrate it, it turns white.
Oh, we did do that.
Yeah.
Mhm.
Yeah?
Yeah, we did.
Yes.
So that's the reason
Lovely
because it's
color.
blue. You see?
Can we do that?
Not now, but yes, we can. So that's the reason because it has color. So, the color in the compound that we have is, this is one of the explanations that we have about the color of the compounds. Obviously, this is only for inorganic molecules. The color in organic molecules is because of another reasons. But today we're going to talk specifically about the color of this. And you know, there's a very cool laboratory actually. When I was in my synthetic inorganic laboratory in the university, I make a project about thermochromic compounds. And this is very nice. Let me see here. I think it's the third video. And there's compounds because this is like the general idea. But actually, I took a course about this. It's very, 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 and I actually teach this thing before. It's very big. And I only have like 4 slides because this is the only thing that you need to know. But actually, you remember about the geometry of the molecules.
Yes.
That you can have a square planar, tetrahedron, and all these things. So there are certain kind of molecules that actually in room temperature, they have one configuration. And then if you increase the temperature, they're going to change the shape. So in my case, I don't remember the exact compound, but I can check. I synthesized one compound that at room temperature was blue, and then when I heat it up, is pink.
Oh, that's cool.
And it's like the same principle that has this, have you ever seen these cups that when you put hot water, they change the outside, they have some color change?
Oh, yeah.
Oh yeah, like instantly change to like
Oh,
clear to
that's
black.
cool.
So this was the project that I synthesized, I think, 3 or 4 compounds that has this behavior. And the change is because the compound at room temperature is a square planar, and then when you increase the temperature, it's tetrahedral.
That's cool.
So like kind of forms together like
Yeah.
nanobots or something.
So they change the color. So let me, I think it's the last video that I put this.
Only one way to find out.
I'll do it.
Oh my gosh.
It's on Tuesday. Oh my God, this is
Our job is to make college easier because students have a lot on them.
Sorry, coach.
Experiment of magnetic
Like
property.
I've restarted it 5 times.
You did nuts.
Types of magnetic property.
Silver tetraiodomercury.
1. Diamagnetic property.
Attention,
2.
mercury salts are highly
Paramagnetic
toxic and can
property.
cause genetic defects. Contact with skin or
First,
inhalation can be
diamagnetic
life-threatening,
property.
and these are toxic to aquatic life with
These
long-lasting effects. Silver nitrate is an oxidizing agent, can cause severe chemical burns on the skin and eyes, and is also toxic to aquatic life with long.
Uh-oh.
What?
Ooh, what?
What is this?
I think we
Never
should
in my life I
reload
saw
the
this
page.
before.
Great. No, how do you like that?
So I can read it? Now I have to switch around everywhere.
What is your
The preparation and properties of silver tetraiodomercurate.
What the
I
heck?
can just edit you like
Attention, mercury salts are highly
Couple
toxic.
inches down, no children. Couple inches up, no air.
Dog's
I
life.
can survive with an error.
Hi everyone, and welcome back. Today we'll be exploring an interesting property of certain compounds called thermochromism. Thermochromism comes from 2 root words, first being thermo, related to temperature, and chroma, which means color. And as you may have guessed, thermochromic compounds tend to change their color with temperature. And by changing color, they change the way that they reflect light. Now this happens because of a change in structure, usually a reversible change in structure, and the compound I'll be showing today is silver tetraiodomercury. This is an interesting compound made of silver, mercury, and iodine, and it is a yellow powder at room temperature, but when heated to about 50 degrees Celsius, it turns to a nice neon orange color. To form the tetraiodomercury compound, I simply need to mix together a soluble salt of silver with a soluble salt of mercury and a soluble iodide. In this case, we'll be using potassium iodide and the nitrates of both silver and mercury, since all of these are very soluble in water. When combined, they form this tetraiodomercury compound, which is insoluble and precipitates, leaving for potassium nitrate behind in the solution, which can then be filtered. Now, it's very important that the silver and mercury compounds are added together first before the iodide, because if the silver and the iodide mix, a large quantity of silver iodide will precipitate from the reaction and no longer really participate. And so, because of that, you can't add this to this. You have to add basically the metal salts first, and then add the iodide later with some pretty rapid stirring to produce a favorable result. Now, I don't actually have silver nitrate nor mercuric nitrate laying around all that, so I'm going to have to make those from the base metals and some nitric acid first. The reaction of the metals, mercury and silver and copper and other things with nitric acid isn't quite as simple as you might think. And in fact, it's more complicated than even depicted here. Now, these depictions are for an idealized reaction with hot concentrated nitric acid, but it turns out that a small amount of NO is also produced in this reaction here, as well as NO2. Now, the NO2 equilibrium is favored more toward hot concentrating acid, and more NO is favored at the cold dilute nitric acid range. So, essentially, in the reaction of these metals with nitric acid, the products are varied by temperature. So further, these NO2s can actually react with water to form more nitric acid, and the NO that I didn't show here, but is also produced, can react with oxygen that might be available in solution from the air and make NO2, which can also react with water to form more nitric acid. So it's difficult to say exactly how much nitric acid you need for this reaction, so it's always better just to use excess. And besides, heating the acid concentrated will also help form these salts much more quickly, and also hot, also help speed up the reaction time. And so that's what we'll do. I'll calculate how much nitric acid I need for the silver and mercury I'll be using, and we'll just heat it up. Heat will also help drive these gases out of solution by reducing their solubility, and then that'll speed everything up, and we'll go ahead and form the tetraiodomercury. Real bit against the silver ingot that I got from the jewelry store. This here is 0.59 grams of mercury, so we'll be right there. We'll measure up like that, but it's doable. And this is 1.95 grams of potassium iodide, to say powder. Now, potassium iodide we'll use later, it's going to the speaker hot water to dissolve for now. The mercury and silver are going to be added to the speaker, whereupon just under 10 milliliters of concentrated nitric acid are going to be added. Actually, this is azeotropic nitric acid at 68%, and really only 2 milliliters is actually needed, but the 10 will give it a lot of extra strength, keep it concentrated, and make this reaction go a whole lot faster. The first thing I'm going to do is add the silver to the beaker, and then add the mercury to that, because an interesting reaction happens. So the silver, you'll notice, is just a pile of dirty, right? When I add the mercury, what known as an amalgam forms. So the mercury goes in, and you'll notice it instantly wets the silver, much like solder would wet a hot piece of copper wire or something. And you see the silver is now sort of very shiny and sticking together into one big clump. And that's because mercury is alloying with silver, and that in fact is the same reaction that when you get a silver filling in your mouth, they actually mix mercury metal with silver powder, and they mix it up very well, and it takes a while for that silver to dissolve in mercury for a mercury silver alloy. And the time that it takes to form that alloy is actually the time the dentist has half the now slushy mixture in your tooth before the alloy fully forms and hardens. And of course, it makes a ratio that stays hard temperature in your mouth, I guess. So essentially what just happened there, it's kind of neat to watch. Maybe that large scale later. Regardless, we now add our potassium iodide solution to the hot water. Nothing spectacular is going to happen here. And then we need a spatula. We're back. Close enough. And it's very soluble in water, so this is going to go into solution extremely quickly. In fact, it's already pretty much gone. Alright, now for the fun part. So I'm going to add nitric acid to this silver amalgam now, and it's going to produce a lot of nitric oxide fumes, and that's why it says heat down here outside, or if you look like I got here. You can see the reaction immediately taking place. You can see here it has dissolved brown gas that nitric oxide is produced.
This guy is going to die soon.
That looks not
You know
safe.
what he's producing here?
Nitrous oxide?
And why this is going to die? What is the risk of the life of this person?
Well, it's deadly in large quantities, so it's like, it'll like shut off your brain activity, and he'll end up just like passing out, and if he has too much, he just completely shut off other organs.
Did you see how many extraction systems he has?
A lot.
No, 0. He doesn't have. He's working outside of the.
He said he had the fume hood on.
Ah, well, I didn't hear about
Yeah, I
that.
think you can hear
You
it.
could hear that?
Yeah, I've watched YouTube in 2 times.
I usually do. I don't have time to do this. So and this guy talked too much.
Yes.
So he's producing. This gas is extremely toxic. So if you are not working enough, forget it. You cannot do this. Or you have to do in a very open space because it's extremely toxic.
Okay, so 30 minutes, you can see that the metals have totally dissolved in nitric acid, leaving a clear solution of silver and mercury nitrates. I also heat this up to drive off the excess nitric oxide, which clears the solution up from a sort of yellow orangey color to pretty much clear. This is the potassium iodide solution we made earlier, and we'll combine the two to form a tetraiodomercury compound. But before I do that, I do want to mention that this does contain soluble salts of mercury. That's very bad for the environment, or very bad to release to the environment. So you want to decontaminate this beaker. If you're going to try this, you have to decontaminate this properly, do a heavy metals waste bin, same with everything I'm going to be using from here on out, including the filtration stuff and all that. So just thought I'd mention that. Anyway, we can go ahead and combine these two. We should notice, if you roll this, yellow precipitate. Let's stir this. And you actually notice thermochromism there because this solution is quite hot. And over 50 C is a striking orange compound, so you can kind of tell already how it's going to turn out. And it's really neat and isolate because if you look, it's so heavy and precipitate that it basically just falls right to the bottom of the beaker. You can see there underneath the solution. And so it's really easy to decant. So I'm going to stir this for a little longer. Alright, so let the solution sit for about 5 minutes. So you can see that the precipitate has largely fallen straight to the bottom. And so what I'm going to try to do, in the interest of not contaminating a whole bunch of my glass or mercury compounds, I'm going to actually decant as much of this liquid I can off of this, and then I'll go ahead and dry what's left by scooping it onto some corded towels. That's a lot better than contaminating a whole bunch of suction filtration equipment with mercury compounds, which will later be decontaminated, which is a reagent and time-intensive process. So we're going to use as little glass as we can in this prep here. Just we decant as much as we can, not really worrying about wasting a whole bunch of it. Because not only for quantitative, you'll hear both of you just trying to get something. And there we go. So we're found here. That still has a lot of nitric acid in it. So I'm going to go ahead and add just a small portion of distilled water, swirl around, and then decant again. Okay. So here's the distilled water. I'm just going to wash this really fast, try and get as much of the nitric acid out of it as we can. And there we go, that's our raw material. Now simply scoop this out onto a paper towel to dry. Okay, I've gone ahead and shut off the fuel because it's noisy and there's no more danger of nitrogen oxides flying around. And I'm sure you tried to put that in a previous video, actually I think several previous videos, that deal with drying powders in a timely manner. The easy way to do it is just to get a couple paper towels, fold them into a packet like that, and then take a coffee filter and put that on top. You scoop your compound into here, and the water gets absorbed into the paper. And it heats and cools extremely quickly, and so the effect is really easy to see. So I have here this heat gun, just basically glorified hair dryer, and I'm going to pick this up, and I'm going to apply heat to this hot air, and you'll see it change very rapidly from a bright yellow to a dark orange. We'll do that a couple times. Bright yellow. Neon orange. Wait around a little bit. Bright yellow. Neon orange. Bright yellow. Oh, my gun just exploded. Did you hear that? Yeah, I'm not really sure.
Thank you, guys. Very slow.
Oh,
So
that was
this is
cool.
cool. And you see how
Is
easy
that
it
the
is to do this kind of compounds. It's extremely easy. It's mixed two things and that's it.
My Hot Wheels cars used to do that.
Sorry?
I had Hot Wheels cars that change color depending on the temperature.
Now you know the secret.
That's how they do it? Okay.
Yeah, they have a certain kind of thermochromic compound and then they change the temperature. And
I
that's
also have a spoon that does that. It goes from yellow to green. Well, if it's cold.
yeah, there's like the video is full of, well, hopefully these guys only do one, but there's a whole, when I studied this, I make only 4, but my God, in my research, I found like at least 100 compounds.
Mm-hmm.
So this is really cool, and I think we have everything to prepare this. So if you're interested, you can come on Thursday to prepare the thermochrome.
Practically do my DE.
Okay.
Can we do this? I'm doing this with glow sticks. Well, not this. It's definitely not this dangerous. But I'm going to do glow sticks, and I'm probably going to heat it up and cool it down to see if it affects